In this lesson, we're going to be looking at page replacement algorithms. In the last lesson, we looked at virtual memory and how paging, or in-demand paging in particular, could be used to supplement the RAM that you've got in your system. So if you've got about 8 GB of RAM, you could extend that by creating a swap space on your hard drive, and that could be used to extend the memory. But when a task is ready to run, those pages that are relevant to that particular task need to be loaded into the RAM. So those can be fetched, decoded, and executed. And for that, there are a lot of different types of algorithms that can be used. Now think back to what we were doing with process management a couple of lessons back. There were algorithms there like round robin, first come, first serve, shortest job remaining, and so on. And similarly, when we are replacing pages, there are a lot of different algorithms that can be used to make the process more efficient. Now, before we begin looking at these algorithms, it's very useful for us to go through some key terms. So let's start by looking at those. So do pause the video and jot these down. These are very important because they often come up in exams as 1 or 2 mark questions. Now, thrash point, we missed this one last lesson, so it's there on screen. It's a point at which the execution of a process comes to a halt since the system is busier paging in and out of memory rather than actually executing instructions. So it's too busy swapping pages rather than doing any actual processing. You want to avoid this thrash point. Page replacement occurs when a requested page is not in memory and a free page cannot be used to satisfy the allocation. So you would need to replace the frame that's in the RAM with the relevant page that you need. So one of the pages needs to be swapped over. And a page fault occurs when a new page is referred to but is not in memory. So the computer wants to access a particular page, that's on your swap space, it's not in RAM, that's when a page fault occurs. First in, first out page replacement is an algorithm that keeps track of all the pages in memory using a queue type structure. And the oldest page at the front of the queue is the first one to be removed when you want to add a new page. Bill-Lady's anomaly is a phenomena which means it's possible to have more page faults when increasing the number of page frames. Optimal page replacement is an algorithm that looks forward in time to see which frame needs to be replaced in the event of a page fault. The least recently used page replacement algorithm looks at the pages which haven't been used the most, and those are replaced first. And then finally, there's also the clock replacement algorithm, which uses a pointer-based system to replace pages. So let's start with page replacement. Page replacement occurs when a requested page is not in memory. If you remember the flags that we were looking at when we were discussing pages, there's a flag that's called P, and that's set to 0. That means that this page is not in the memory, but it's in the swap space. So when paging in and out from memory, it is necessary to consider how the computer decides which pages are replaced, and then it allows the requested page to be loaded. When a new page is requested and it's not in memory, a page fault occurs and the operating system then replaces one of the existing pages, which is in RAM, with the relevant one on the swap space. Now, how you decide which page to replace is often done in a number of different ways, but all the methods have the same goal, which is minimizing the number of page faults. And a page fault isn't really a fault, but it's an interrupt that is generated by the hardware saying, well, I want this piece of data, I want these instructions, they're not there in RAM, could you do something about it? So when a running program accesses a page that is mapped into the virtual memory address space, but it's not loaded into the actual physical memory, then the hardware needs to raise this page fault interrupt. So it all comes back down to interrupt handling in a way. Now let's start by looking at these page replacement algorithms. We have the first in, first out, FIFO, which is pretty straightforward to explain. The oldest page is at the front of the queue and is the first one to be removed when a new page needs to be added to RAM. Now, FIFO algorithms do not consider page usage when replacing pages. A page may be replaced. It might be the most often used page in memory, but because it arrived earlier than everyone else, it gets replaced first. Now, this suffers from what is known as Bill-Lady's anomaly, a situation in which it is possible to have more page faults when increasing the number of page frames. Because if the first page was the most used page, and then the CPU wants access to that page, but you don't have that loaded in RAM, it's going to generate a page fault. Now, the ideal situation is that as the number of frames increase, you want to reduce the number of faults. However, Bilady's anomaly occurs when you're increasing the number of frames, but the number of page faults keep on increasing as well. And we want to avoid that type of situation. The next algorithm we're going to be looking at is the optimal page replacement algorithm, and this one is a hypothetical one. It's impossible to implement because the operating system generally has no way of knowing when each of the pages will be replaced next. So we use this one for comparison studies to measure the effectiveness of all the other algorithms. This algorithm has an advantage that it's free from Bilady's anomaly and has the fewest page faults, because if you could predict which page is going to be loaded next, you would already have that page replaced in RAM. So that means when the processor needs that page, it's always available. So just remember that this algorithm is hypothetical and it's used for comparative purposes only. The next algorithm in our list is the least recently used page replacement algorithm, and this is again very straightforward to explain. The page that has not been used for the longest of time is replaced. To implement this method, it's necessary to maintain a linked list of all the pages in memory, with the most recently used page at the front and the least recently used page at the rear of the linked list. And that's the most simplest way of implementing an LRU algorithm. The final algorithm on our list is the clock page replacement, which is sometimes also called the second chance page replacement algorithm. Now in this one, we use a circular queue, so the diagram on the top right kind of gives you an indication of how that will be. So a circular queue structure is used with a single pointer serving as both the head and the tail of the queue. So when a page fault occurs, the page pointed at that particular point in time is inspected. The action taken next depends on the R flag status, and this is going back to those page tables and page flags that we looked at a couple of lessons ago. If the R flag is equal to 0, the page is removed and a new page is inserted in its place. If the R flag is set to 1, then you look at the next page in the queue and you keep on repeating this until you find a page where R is equal to 0. So what does R equal to 0 means? It basically means that the page is in the read-only state, and that's the page that we can simply replace. If a page is in the read-write state, that means that it has something that we might need to write to, so we don't want to replace that. Therefore, we move on to the next page until we find the one that's read-only, and we replace that. Now, in all page replacement methods, when a page fault occurs, the operating system has to decide which page to remove from the memory to make room for a new page. And this is done by swapping pages from the backup store to main memory and vice versa. All algorithms do the same thing. If the page to be removed has been modified while in memory, for example, we call it dirty, it must be written back to disk. So you can't just simply discard it. You have to write it first, and then that's the end of that. If it's not been changed, then we just don't need any rewrite and we can just discard that. That's the point of the D flag. Now remember that page faults are not errors. These are used to increase the amount of memory available to programs, especially those that utilize virtual memory. So never call them errors, okay? These are just interrupts that we can use to manage memory efficiently. Now to summarize the basic differences between processor management and memory management, on screen you see a nice diagram. Process management allows you to do multitasking, and we manage processes using scheduling. Memory management allows us to partition memory so we can ensure that the right data and instructions are always available to the processes. And we use two techniques here, memory paging and memory segmentation. So do pause the video and understand this diagram carefully, and hopefully this makes the differences clear between process management and memory management. Both are required and both are essential to the efficient and stable running of any computer system. And with that, we'll draw this lesson to a close. Hopefully you understand how page replacement algorithms work. You should be now familiar with first in, first out, optimized page replacement, least recently used page replacement, and clock page replacement algorithms. If you do have any questions, do get back to me. Otherwise, I'll see you in the next lesson.